So when an acid is titrated against a base and the pH is measured, we can get a graph or a curve, and we call that a titration curve. Now there's 4 types of combinations of titration curve. You could have a strong acid being titrated against a strong base, we call that SA versus SB, a weak acid versus a strong base, a strong acid versus a weak base, and a weak acid against a weak base. And there's a variety of things to consider. First of all, we need to look at what is in the beaker, what is the analyte, and that will determine the pH, the initial pH of your pH curve. And then you need to look at what is present in the burette. Let's see if we look at some examples. From my previous video, you will also know how to choose an indicator, and for this purpose we'll just remind ourselves of the 2 major indicators. Remember, the indicator has to change over the vertical part, or the equivalence point, and therefore for a strong acid, strong base, from my previous video you learned that both phenolphthalein and methyl orange were suitable indicators. For a weak acid, however, we can't use methyl orange because it's already yellow at that pH, and therefore phenolphthalein is a suitable indicator for a weak acid and a strong base. If we now go to the converse, where we've got a strong acid and a weak base, we can use methyl orange but not phenolphthalein. And finally, neither indicator is useful for a weak acid, weak base. In our first example here, we have a strong base being added to 25 centimeters cubed of the acid. So the base is going to be in the burette because it's being added to 25 centimeters cubed of the strong acid. Both solutions are of equal concentration. So if they're of equal concentration and it's a 1-to-1 ratio, then it's going to take 25 centimeters cubed of the base to neutralize the acid. We haven't been given the concentration of the acid here, and we haven't been given the concentration of the base, so we'll just estimate, because it's a strong acid, its pH is roughly 1. So these are estimates, and a strong base is roughly 13. So an excess of the base is going to give us a pH of roughly 13. Now it's really important to notice that this point here, the vertical part of the curve, is produced when a very small volume of the base is being added. There is a rapid increase in pH as the equivalence point is met, and then as there is a slight excess of hydroxide, it rapidly becomes very alkaline. So this is the equivalence point. The second titration curve here is, this time we've got a strong base in the burette, but we're adding it to a weak acid, and the weak acid this time is in the beaker. We've got 25 cm cubed of the beaker. Assuming it's sodium hydroxide and ethanoic acid, they react on a 1-to-1 ratio, and therefore you're going to need exactly the same volume if they're both the same concentrations of the acid to the alkali. So the equivalence point is here at 25 centimeters cubed. Notice the difference here. Because it's a weak acid, it's going to start off at around pH 3 rather than pH 1. And it's still a strong base, so it's going to be equivalent. It's going to be in excess around 12 to 13. But again, we have a vertical point. It's really important that you have a vertical point where we have equivalence, where just 1 drop of sodium hydroxide will rapidly increase the pH as it's in excess. In this next scenario, we've got a weak base, which is ammonia, and that's being titrated against a strong acid. Again, both the same concentration, so the volume of acid needed to neutralize the base is going to be exactly the same, 25 centimeters cubed. Again, notice this is vertical. The pH of the acid doesn't increase very much until we hit equivalence point, and then a couple of drops of ammonia will send it over. And because it's a weak base has got pHs roughly 9 to 10. And then in the final scenario, you've got a weak acid and a weak base. The weak acid is in the beaker here, and the base again is in the burette. So what happens if we flip the beaker so that the analyte this time is the alkali and that the titrant is the acid? We just get mirror images. So let's have a look at some examples that you can work out yourself, and then you can check your answers. So let's take a stepwise approach. First of all, we've got nitric acid, and it tells us that this time the potassium hydroxide, there's 30 centimetres cubed of it, is likely to be in the beaker. And remember, you would have used a pipette to put the potassium hydroxide in there. The acid is nitric acid, and that is in the burette. So as the acid is added, the pH is going to decrease because you're adding an acid to an alkali. Now if we look at the equation for the reaction, the nitric acid containing the hydrogen ions is reacting with the strong base, which is the potassium hydroxide, and they're reacting a 1-to-1 ratio. So if we use our initial, our change, and our end, we can have a look at the amounts of each of these during the titration. So we're told that the volume and the concentration of potassium hydroxide, and therefore we know the initial amount or the number of moles of the potassium hydroxide. And the amount of moles of potassium hydroxide is concentration, which is 0.5 times 30, and then we'll times by 10 to the minus 3, because we need to convert our volume into dm cubed before we can find moles. Because these two react on a 1-to-1 ratio, that is exactly the same amount as the hydroxide ions. So at the equivalence point, there'll be exactly the same number of moles of acid that have reacted with the potassium hydroxide. So the first thing is to find the volume of the nitric acid that's needed to react with our potassium hydroxide. Well, we've been told that the concentration of the acid in moles per dm cubed is 0.1, and therefore we can find the number of moles of the acid. So we can find the titration volume of the acid because we know the volume is equal to the number of moles divided by the concentration, and therefore the volume of the acid that we need at the end point is the number of moles, which is 0.05, times by 30 times by 10 to the minus 3, and that is divided by the concentration, which is 0.1. Now that will give us the titration volume, or the end point or equivalent volume, which is in dm cubed. So let's now convert that to centimetres cubed. So the end point volume is 0.015 dm cubed, but let's keep it in centimetres cubed, depends how you want to label your graph. So we know it's a strong acid, strong base, and we've been told that the potassium hydroxide has a pH of 12.7. So we know the initial pH. What about the final pH? Well, the final pH is going to have a massive excess of nitric acid, and therefore the final pH is going to be acidic, and we can roughly guesstimate this. So it doesn't, remember, these are sketches, so the final pH is going to be an excess of the nitric acid, which is roughly going to be 0.1 moles per dm cubed. And therefore the final pH is minus log of 0.1. So the final pH is going to be 1. So what we have now is our end point volume, the equivalence point, that's 15 centimetres cubed for the neutralisation. We have the start pH and we have the end pH. Now we can plot our graph, or sketch the graph. On your graph, remember that the x-axis is the volume of the acid that's being added, so that is your nitric acid, and that's in centimetres cubed. The y-axis is increasing pH. We knew the start pH, we were told it was pH 12.7, so it's roughly there. That decreases slightly until it reaches what is called the equivalence point, and at the equivalence point the moles of hydrogen ions is equal to the moles of hydroxide ions. Just a couple of milliliters later is an excess of hydrogen ions, so the pH then drops rapidly. to here, and that is at 15 centimetres cubed. Now we can see that the pH then levels off to roughly about 1, because that's roughly the pH of an excess of the 0.1 moles per dm cube nitric acid. And because this is a strong acid, strong base indicator, you could have either chosen either phenolphthalein, PHTHLEIN, or you could have chosen methyl orange. Either indicator was suitable because their endpoints change well within this vertical part of the curve. This here is a strong acid, strong base. So this time we've got sodium hydroxide in 20 centimetres cubed of nitric acid. So the 20 centimetres cubed must be what is in the beaker. So this time the acid is in the beaker and the sodium hydroxide is in the burette. So let's do our calculations again. Since it's a strong acid and it's a strong base, let's see how many moles we've got. Well, we know the amount in moles is concentration times volume, and we know that the nitric acid is 20 centimetres cubed, and that's its concentration. So that's 20 times 0.15 times by 10 to the minus 3. Because it reacts in a 1-to-1 ratio, that must also be the amount of hydroxide ions that are reacting at the end point. And we know the volume, because the volume of our nitric acid is 20 centimetres cubed. And to therefore find the volume of our hydroxide, we know the concentration. The concentration of our sodium hydroxide is 0.1 moles per dm cubed. And therefore we can find our volume because we know that volume is number of moles over concentration. And the number of moles is 20 times 0.15 times 10 to the minus 3 all over 20. And that will give us our volume in decimeters cubed. Now, the sodium hydroxide is going to be in excess at the end, and therefore we want to know our final pH. Because we've got alkali in excess, we're going to use Kw is equal to the concentration of hydrogen ions times the concentration of hydroxide ions. And therefore we rearrange this to get our hydrogen ion concentration, which is Kw over the hydroxide ion concentration. Remember, Kw is equal to 1 times 10 to the minus 14 moles square of dm to dm to the 6. Our hydroxide ion concentration, we're told, is 0.1. So that gives us a value of 1 times 10 to the minus 13. And pH, remember, is minus log of the hydrogen ion concentration, which is 1 times 10 to the minus 13. So our end point, roughly, when there is an excess of the strong base, is going to be about 13. Remember, these are guesstimates for sketch curves. So what do we have? We know the start pH is going to be acidic because the nitric acid was in the beaker. And we know roughly that the pH of a 0.01 molar concentration of acid is going to be 1. So we know the start pH, we know the end pH, and we know it's a strong acid, strong base, and we also know the volume needed, the volume of sodium hydroxide needed to neutralise that acid is 0.03 dm cubed or 30 centimetres cubed. So that comes out at 0.03 dm cubed, and to make it look nice on our titration curve, because our burette we're adding in centimetres cubed, convert that to centimetres cubed. So you need to know the start pH, we need to know roughly the end pH, and we need to know the titration volume. You need to know for a pH titration curve roughly the start pH, remember roughly, which we've got here, the end pH, which we said is about 13, and we need to know the equivalence point is 30, that's the volume needed to neutralise all of the acid, and that is vertical. This is a strong acid, strong base titration, so again you could use either methyl orange or phenolphthalein. This next pH, this time we've got a strong base because it's sodium hydroxide, but we're adding it this time to a weak acid. We've been given the pH of the weak acid and we've been given the concentration of the sodium hydroxide. So we know the basic shape of the curve. Let's now find our amounts. So again, it's a 1-to-1 ratio, and it's sodium hydroxide, our hydroxide ions, and it's our acid, which is ethanoic acid, but they're still reacting on a 1-to-1 ratio. So the initial amount in moles, which is concentration times volume, we know is of the acid. So that's 20 centimetres cubed is the volume, 0.150 is the concentration, times back to 10 to the minus 3 to get our volume into dm cubed. The number of moles of acid at equivalence point must equal the number of moles of sodium hydroxide. So that is exactly the same. That's 20 times 0.15 times 10 to the minus 3. We also know the concentration of our sodium hydroxide. The concentration is 0.200 moles per dm cubed. And therefore we can find that the volume of the sodium hydroxide needed to neutralise, because we know that volume is the number of moles divided by concentration. So that's 20 times 0.15 times 10 to the minus 3 all over the concentration, which is 0.2. Converting that back to centimetres cubed is 15 cm cubed, because the answer to that is 0.015 dm cubed. What about pH? Well, we know we're going to have sodium hydroxide in excess at the end. So the end pH, we need to use Kw is equal to the hydroxide ion times the hydrogen ion concentration. And rearranging that, hydrogen ion concentration is equal to 1 times 10 to the minus 14 all over the hydroxide ion concentration, which is 0.2. Converting that to pH, taking the minus logs, the end pH is equal to the minus log 5 times 10 to the minus 13, and that comes out at 13.3. So we've got our end pH, our start pH, this time we've already been given. So our start pH is 2.8, and it's a weak acid and a strong base titration. The neutralisation volume is 15 centimetres cubed. So remember the axis there is volume of sodium hydroxide in centimetres cubed. This is the pH, and we know it's starting off at 2.8. So there's pH 1, there's pH 2, there's pH 3. So there's 2.8. Now, the equivalence point is 15 centimetres cubed. Now remember that the pH increases gradually because it's behaving as a buffer solution. The pH is going to end, as we've calculated here, roughly about 13. And there it will level off. At this point here, it's vertical. And it's a weak acid, weak base titration. This time we have a weak acid and a strong base. So this time we can only use phenolphthalein and not methyl orange.